So hi everyone. So this is a recording of the workshop that me and Samuel gave, First Steps into Open Science, on June 8th at the Unique Student Symposium. And in the spirit of open science, we wanted to make all of the content available to the public. So welcome to this workshop. So me and Samuel are both students at the University of Montreal, currently doing research in cognitive neuroscience. I'm working in genomic imagery, and Samuel is doing work related to concussions. So we are here today on the behalf of OZUM, Open Science UMontreal, which is a student initiative that aims at promoting open science, giving out resources to the community, and also engaging with the community.
I'd like to give a shout out to Open Life Science, which is a program, a 16-week-long mentorship and cohort-based training on open science, in which we share expertise and gain knowledge essential to create, lead, and sustain an open science project. So feel free to visit openlifesci.org to know more about this great initiative.
We also invite you to check out our repository, which is OS for Neuro-AI, in which we are trying to gather resources for the Neuro-AI students out there to make the process of their research more open. So if you want to contribute, you can just log onto your GitHub account and submit a pull request, and we'll make sure to merge any suggestions and resources that you add. So what we'll be covering today. So first we will talk about what is open science, which is something that can be quite confusing at times. We'll talk about science in the context of today, which is connected world, and we'll talk about the ethical implications and considerations to keep in mind. We will also talk about the reproducibility in research. We will give some tools and concrete guidelines as to how a student can apply open science to their own research, and yeah, that's about it. So before we start, we ask you to think about what comes to mind when you think of open science.
So you can pause the video if you need more time, but we're just gonna get started with the talk itself. So there are many reasons why it's important to define what we mean by open science when we speak with others. First, simply because open science can mean many things depending on the context, the individuals, even the organizations and the fields, and even countries. It's even too vague, according to some, that like Tal Yarkorny, which is a prominent researcher in neuroscience and neuroimaging, who has done his fair share in open science work, and in his blog post titled "I Hate Open Science," is arguing that the term is just too confusing, and maybe we should be more precise when we talk about it. But there have always been many definitions regarding open science, and there's not one formal definition accepted by the community. But that's good. Some people argue that because the open science is a movement, and above all a social movement, this social movement brings together individuals, groups, and communities with similar but not identical values, priorities, and ideas. So that means we just gather all together and we work towards the same thing. And this is this pluralism that gives open science a unique strength to improve science. So I thought about giving just two definition, not pick at random. I chose the first one to be the Wikipedia one, simply because Wikipedia is one of the best initiatives out there that demonstrates the power of a free and open initiative. So basically on Wikipedia, anyone in the society can contribute to it. as long as they have access to internet. Thanks to its openness, Wikipedia has become the largest and most viewed encyclopedia in just a few years, surpassing other proprietary or commercial encyclopedias. So this is just a way to showcase how powerful free and open project can be. So Wikipedia defines open science as the movement to make scientific research and its dissemination accessible to all, which is a straight to the point definition, short and sweet. We like it. However, in Canada, there's a new roadmap for open science that has been published by the government in 2020. And because it's fairly recent, I thought it would be great to showcase what they mean for open science. I won't read the whole definition, but if you, well, you can pause it and read it. But what I like about this definition is they put the focus on three things first. So they're talking about inputs, outputs, and processes that must be made freely available with minimal restriction. There's also another thing important to highlight is the fact that open science must be enabled by the people, technology, and infrastructure, meaning as a community, we need to collaborate to make it happen. So it won't just happen by itself. And finally, I think it's even more important for open science. It's that it must be practiced in respect of privacy, security, and ethical considerations. And I think it's really important, especially in the neuro-AI field, given the sensitive data we work with. So yes, both definitions that we just saw are good. They clearly define what open science means, but there's more to open science than just about the science itself. There's maybe a little bit, there's something missing to really represent what is open science as a whole. So if you're watching this talk, well, it means that you probably have an interest in the impact that open science can have on improving the research system, or maybe you've noticed something about the status quo in academia in general. And what I really like about this conclusion in the Open Innovation, Open Science, Open to the World report published by the EU, the European Union, it's the fact that open science captures a systemic change to the way science and research have been carried out for the last 50 years. So it's all about sharing and using all available knowledge at an earlier stage in the research process as well. And from this, maybe now you're already thinking, or it's getting clearer that open science is about systemic change. It challenges the way research is being conducted at a practical level, but also at a cultural level. So from how do we evaluate research to who can participate or can be involved in the process of doing research. But it's also important to be aware of the geopolitical differences that shape our understanding of open science. For example, in North America or Europe, open science is often marketed in such ways that promote economic value, productivity, and competition above all other factors. Whereas in what is commonly called the Global South, open science appears to be more about fostering community, building through knowledge, sharing, nurturing social networks around new technologies and infrastructures. So it's just to say that despite open science trying to change the system as a whole, we also have to be aware that within open science, there are some power relations and disparities throughout the globe. For example, in their paper blog post, Open Science is Broken Science in 2020, Guess and Whitaker said that the true revolution lies in empowering the historically disempowered. So this is a subject close to my heart, and if it is for you as well, I encourage you to read the two papers listed below, which dive a little bit deeper in the subject. So yes, in open science, community comes first. As I like to call it team science. Open science does give rise to a new set of standards, tools, and principles to revolutionize the way we perform and disseminate research knowledge based on cooperative work. But up to now, maybe you feel that open science seems to be a different way to perform research versus traditional scientific methods, but it's not exactly right. We should see open science more as an enhancement to the traditional process by using new knowledge, skills, and technologies to improve the research ecosystem. So often we can base open science or represent open science on three core things. So namely the processes. So we're talking here about collaboration, reproducibility, sharing, and the products. So about everything open, basically. So from data to code to materials, and the values from accessibility, transparency, integrity, equity, etc. So when we put these three core concepts together, they seem to form a chain reaction to and a positive feedback loop in which a value will drive a particular process. And then in turn, this will scope the products of research. So it's like a loop feeding itself, which is great. And often what's going to attract people to the open science movement is the values that are implicit inside the definition of the term itself. So this is not a surprise. Open science is not a binary concept. It's more a concept with multiple dimensions. We could go from the complete extreme, from everything open to completely closed. And this umbrella is often used to illustrate all the concepts that can fall inside open science. So we've got all the opens on one side, from open access, open data, open tools, open source, which could be traced back to the free software movement, I think from 1984. And we also have all the topics related more to social justice, including citizen science, open collaboration, diversity, equity, and inclusion as well. But open science is not new. Well, we could argue that the more modern open science was catalyzed by open access, mainly because some people were getting frustrated by the way big publisher or commercial publishers were reacting to the growth of internet and the World Wide Web. So basically, many publishers have attempted to maintain a restricted access to and increase exponentially the subscription fees, despite computers and internet enabling wide and easy access to publication and communication. So yes, I'm going to give credit to the publishers because they did add a significant value back when the internet was not a thing, and we needed to print journals on actual papers and track citations by hand. But right now, the flow of scientific information is different. It's no longer limited by access to the scientific knowledge and an increase in so it's no longer the case. So that's why some people were getting frustrated. So researchers have created, for example, arXiv in 1991, and then open access was formally defined in 2002. And then this last decade, there's a growth in preprints, and especially during COVID, we've seen so many thousands of preprints related to COVID. So this is just some example that we can see how it evolved since the creation of internet. And there was also some big institutions who ended their deals with publishers like MIT and the University of California. If you're really interested in the topic and you'd like to know more, there's Paywall the movie, which is a really great movie about the publishing industry and how much money they make out of our own work that we do for free. But in parallel, there was an explosive growth in the development of different aspects of scholarly infrastructure. So how we do research and how we share research. And thanks to the web, it really enabled us to instantly share and collaborate at a global scale. So just as a fun fact, internet and the World Wide Web were invented by researchers for researchers, simply to share data easily and at low cost. And one thing that we should keep in mind, especially if you're watching this talk right now, is, it means that you have access to internet, but that's not the case everywhere. Not everyone has access to internet. But the founder of the World Wide Web, Tim Berners-Lee, made sure that the internet, the web, shall I say, is he really wanted it to be a universal space. But he also said that to be a universal space, nobody can be in control of it, meaning that it should be a free project. So he made sure to give a free license to the web itself versus being proprietary. So that's something to keep in mind, because we are privileged to have access to the web and share information pretty much everywhere we go, especially in Neuro-AI. That's another thing Andréanne is going to talk about soon enough, about the digital divide.
Yes, so today science is very different from what it was 50 years ago. So we call the science that we're doing networked science, which is science in the context of computers and the internet. So it's very safe actually to say that most experiments today are using at least partly these technologies. And this has actually increased the possibilities for open science. So it's easier to document experiments. It's easier to collaborate, to share information with other researchers and also with the public. Technically, it's made scientific publication easier to access, but as we have seen earlier, this is not always the case in practice, especially with the paywalls. Then the question that we can ask is, if these tools and means are available, then what exactly is the problem here? Well, in this connected world in which research is becoming more and more dependent on technologies, there's this whole other dimension to open science that we need to be aware of and that we need to talk about, and that is the ethics of usage and accessibility of these resources. So here on this slide, you have, so this is to show that even as we have more and more internet users over the years, there still remains big disparities in terms of who has access to these resources. Here you have the percentage of the population throughout different countries in the world that are internet users. And as you can see, it's very unequally distributed. So if you compare Africa to Western countries, you have up to 4 times more users in the more Western part of the world. Another point of concern that's especially relevant in AI research is the unequal access to compute power and resources. So today, the ability to compete in the field depends on the access to compute resources. And this statement is increasingly true as the field is progressing. So it's estimated that computing cycles consumed by the largest AI training models have been doubling every 3.4 months since 2012. And the computing resources are very expensive. So what we want to avoid is that in the long run, only the richest firms, richest countries and universities are the ones that can contribute and compete in modern AI research. So here's to give you an idea of the scale of resources that are required in deep learning. So to train the state-of-the-art models, for instance, the GP3 model, which came out in 2020 and is used for natural processing language tasks, we end up with 175 million parameters. It's estimated that it takes up to 355 GPU years, $4.6 million to train this model, even with the lowest priced GPU cloud on the market. So those are enormous resources. And so a valid question that some researchers are asking themselves is money all you need in the field of deep learning in order to be able to compete in this game? And the reason why we're talking about this today is because it's so expensive and the field is very rapidly expanding. Open science becomes extremely important. So the ability for smaller contributors to take part in the advances in AI, deep learning, but also AI, relies on the willingness of the most fortunate to adopt openness practices, to, for instance, share their models with other researchers. So what a researcher can do is use these pre-trained models and do fine-tuning on them. And also, it also relies on governments giving out compute resources to everyone. So an example of that would be Compute Canada, which enables us smaller contributors to have access to resources.
And are you going to talk about Hugging Face?
So Hugging Face is a tool that can be used for researchers that want to share their models. I think this one is more for transformers, but there are other tools out there that you can use, and I recommend you check that out on your own.
So there are some efforts to increase diversity, equity, and inclusion. This is an example from the psychology field, because they realized that participants who were involved in psychology study were mostly drawn from populations that are white, educated, industrialized, rich, and democratic. And all the participants coming from these populations represents 80% of all participants. But in reality, if you look at a global scale, these weird people only represent 12% of the population. So it's not representative at all. And to make matter even worse, we've noticed that these weirdos and weirdas, they represent some sometimes outliers values on some measures. So it's not even well, representative of people on a normal curve, which is well, it could be well, it could introduce some bias further down the pipeline. So basically, this is just a good reminder that biases from samples can be translated into results, which can then be become application in the real world with real consequences, but it doesn't take it doesn't give the proper picture or the big picture of what's happening in the population. So as an example, we've got here the Psychological Science Accelerator, which is a globally distributed network of psychological science lab. We're talking about more than 500 labs, and they represent more than 70 countries on 6 continents. So they try to coordinate data collection for democratically selected studies. So meaning that everyone has their say into what they're going to study and make sure they represent the global population. There's also the framework for open and reproducible research training, which aims to get more, gives and try to inspire teachers and professors to include more open and reproducible research in their courses. Talking about bias, well, we can easily find examples of coded biases in the AI. Like, for example, on the left here, we can see that that Amazon ditched their AI algorithm that was recruiting more men versus women for technical jobs. This is just one example of many. We also have another example here where in which facial recognition wasn't really good wasn't good at all at detecting darker skinned women's face. That was highlighted in the documentary Coded Bias that is now available on Netflix. But biases can also affect more than physical attributes. For example, here, researchers from Stanford found that state-of-the-art automatic speech recognition systems misunderstood Black speakers twice as often as white speakers. So this is important to keep in mind also that biases are not only in data, they can also be implicit to the person conducting the research or writing the code, and this can add up and producing some scary biases in the end when we try to apply this, let's say, for facial recognition or getting a better understanding at the human level.
So another important concept is the black box concept in AI, which refers to a system that is so complex that it's very difficult to understand how we are going from an input to a certain output which is very often a decision. The reason why it's important is that very often AI research, as Samia mentioned, will lead to real-life applications. For the healthcare system, it could lead to systems that help with diagnosis. So in the case of these black boxes, where we have algorithms that are actually, we don't really know what information these algorithms are using to reach a certain decision. So the danger with that is that it leads to over-dependence to technologies, and also that it leads to certain biases that sometimes we are not even aware of, such biases that we have seen previously. So we have to weigh out the advantages of what a system is giving us, for instance, better accuracy, and the problems that could be caused by the obscurity of the decision-making process. So now for this next part, to start with, we would like for you to think about a time that you've tried to reproduce somebody else's results and not achieve the same results. Or if you know of someone that has failed at reproducing the results of somebody else's experiment.
And if you do know someone, know that you're not alone.
No. Okay, so for this next part, open science as a means to save science. So we will talk about reproducibility in research. So one of the reasons why we need open science is because of the reproducibility crisis we are currently facing in research. But before diving into it, what exactly is reproducibility? So it's when a researcher conducts a study using the same materials to reproduce the results of an experiment, often an experiment that was published. And the reason why we need reproducibility is because, well, that's at the core basis of science as being a self-correcting system. So by reproducing experiments, we are able to weed out results that don't stand up and add more evidence to existing results as well. So in other words, it's helping us build the credibility of science as a whole. So are we in the middle of a crisis? Well, there's this phenomenon that we're observing where there's a huge amount of studies for which we're not able to replicate the results. So according to this survey published by Nature in 2016, at least 60% of scientists responded they had failed to reproduce the results of another researcher, and 40% the results of their own study. And there was also this huge Project Reproducibility, where a group of scientists tried to replicate 100 studies in social psychology that had been published in big scientific journals. And turns out that out of the 100 studies, there were only 36 that replicated. So in the same study published by Nature, they also asked researchers if they thought that we were facing a crisis, a reproducibility crisis. And 52% of researchers agreed to say it was a significant crisis. 38 agreed we were facing a slight crisis. So we can see that it's a consensus according to that study in the scientific community. So how exactly did we get to that point? Why are we facing such reproducibility issues? There are many reasons for that. So a couple of them, well, first of all, questionable research practices, so such as p-hacking, harking. We have publication biases, the publisher-perish culture that's very big in academia. There's data and software issues also that can lead to lack of reproducibility. And a very important point is the lack of transparency. Science involves sharing enough detail about how research is carried out to enable other researchers to replicate it. So without that, it becomes very difficult to reach similar results. So what about transparency in AI research? So AI and computer science have very strong foundations on collaborative research. We just think of open source. However, just because open source is part of the culture does not mean that the AI community is more transparent when it comes to sharing their research. Actually, if you look here on the figure, so this is from a paper and it reports, it's a percentage of published papers that are sharing details for variables in their methods, data, and experiments. And as you can see, the percentages are quite low. In some cases, as low as 1% of papers documenting a variable. So overall, we find, overall in research, we find that there's a lack of consistency with regards to the way research is shared. And this is true, so in research in general, but also for the AI community. And this is especially true for research in industry, where there are no clear standards and where the product of research is also mixed with monetary stakes. So there was a lot of criticism directed at science conducted in the industry in the past years. And a good example of that is this paper that came out by Google that was published in Nature, which was describing successful trials of an AI that was looking at signs of breast cancer in medical images, and that could, in certain cases, outperform radiologists. So what exactly was wrong with that paper? Well, the problem was that the team provided so little information about the code, how it was tested, that it was basically not reproducible. And in response to that paper, 31 researchers also published a paper, once again in Nature, in which they criticized that paper, did some recommendations for transparency and reproducibility. And they also said that this paper was not worth anything scientifically. That it was yet another example of a very high profile journal publishing a very exciting study that has nothing to do with science. But The irony in this story is that, well, the response was published behind paywalls. So why do we care? Well, because without transparency and without openness, we are not able to verify science, we are not able to trust science, and because of that, well, science kind of loses its credibility. So I also want to mention some efforts towards reproducibility. So there are lots of them. We now have checklists that you can use to make sure that you're reporting everything in order for your experiment to be reproducible. We have reproducibility challenges that have been introduced, in which researchers try to replicate results of published studies. We also have initiatives such as Papers with Code, where researchers can link a study to the code that was used for the experiment.
And then we've got other initiatives in open science, in neuroscience specifically, starting with INCF leading many task forces to enable more fairness in neuroscience. So yes, we've got many researchers already doing open science by sharing open source toolboxes, preprints, data, but there's still work left to be done to link all the toolboxes, software, papers, to make sure everything is interoperable. And we also need to somehow set community norms and standards. The other logo here are just to showcase some of these, either standards or other resources. But there's also an important component is how do we teach all of these newly-ish neuroinformatic tools. And Brainac School, which is a 4-week summer school, is trying to do so by teaching students these tools on projects that they're working on, instead of just sharing theory about the tool themselves. And just a small slides on open science and COVID-19, just to showcase how only one crisis has proven the urgency of fostering an equitable access to scientific information, and that with open science policies, we can remove obstacles to the free flow of research data and ideas that can then accelerate the pace of research. So this is really critical. That was critical, or it's been critical to combat COVID-19. And this is just to showcase one of the great papers written by Estrid Jacobson from the QBIN, so the Quebec Bioimaging Network. So I encourage you to read it. The links are all going to be in the description of the video.
So now, how can students in Neuro-AI make their science more open? So we have here a few tips, a few tools that you can apply to the process of your research. So first of all, transparency is a keyword that you want to keep in mind. So it applies at every step of the research process, from generating a hypothesis to reporting your study. So the first thing that you want to do also is to think about licenses. So traditional copyright is the default in most countries. So if you want for another researcher to be able to use your content, modify it, you need to explicitly specify the copyright license. So there are a few of them. You have Creative Commons, MIT, Apache for open source. You can visit the link on this slide if you want to learn more about these licenses. You can make it open source, so make your projects open source. And this starts with choosing the right license. In theory, then anyone that has the skills and motivation can contribute to your project. You can also contribute yourself to open source. so other people's projects. You also want to think about how you want to organize your projects and do that ahead of time. So there are lots of tools out there that exist that can help you with experiment management. For instance, in machine learning, MLflow, which helps you with benchmarking. There are project templates that you can custom made, for instance, cookie cutter, data management. You also want to think about data management, and you ideally want it to follow the FAIR principles. So this is findable, accessible, interpretable, and reusable. And look to see what is the standard format for data in your field. So in neuroimaging, for instance, we use the BIDS format. And this is very helpful, especially when you want to share data with other researchers.
And also just make sure to be as open as possible, but as close as necessary, because the data we deal with sometimes have privacy concerns. So just to make sure, always check with your ethics committee before sharing your data.
So to facilitate collaboration, you can use notebooks or tools like Github. So Github enables you to create open repositories. And so in theory, anyone can then add on to your project to make it better. You can share your environments. Everyone that conducts an experiment has a very specific environment, whether it's in terms of operating system, in terms of the libraries that they're using. And so you can isolate your environment and share it. There are different degrees to which you can do that. I invite you to look at these resources on the slides of Docker, Conda, and Singularity. And the reason why you want to do that is because, well, across different environments, you will reach different results. So if you want another researcher to be able to get to the exact same results, well, you need to share that environment. So here you have, this was a paper that showed that just by varying the version of the operating system, you were obtaining substantial differences in volume differences in, I think it was anatomical volume measurements of the brain. You can use version control that enables you to track the changes to your project so that you can always go back in time. And when you share that, people can always see where your project was at any point in time. And this is being very transparent. So you can do that for scripts, notebook, text files, data. Here are some resources. So Git, you can use Git with GitHub. So yeah, you can change slides. Also share. So share, basically it's share everything. So share your code, your models, your data. All the details. So sometimes details is what will make the difference between a model working and a model not working, and deposit that on open repositories and platforms. And here we have a few platforms that enable you to do that.
You also want to share your published work as much as possible in open access journals. Here, DOAJ is the directory for open access journal. So basically, you can find a nice little home that is open for your work. And for sure, try to preprint your work as well. So if you cannot publish in an open journal, you can preprint it. So it's called the green open access route. And this way, if you preprint, it's going to make even research faster because people have access to your work 1 or 2 years even sometimes before it's going to be published in a journal. So here it's just to showcase some people who've pushed open to the extreme. So I'm going to start with talking about what Greg Kiar, a former neuroscience or IPN student at McGill, has done. So he's done an open PhD. So yes, he did publish all his work openly, but he also shared his thesis and all the funding he's tried in the past So let me know if we can see the window or we cannot. Okay, so here you can see all the documents he shared in the past, whether it was funded or not, which is really great. And here you can see it was unfunded, but most of them was funded. But so for new students, it's great because we can read it and be inspired about how we can implement those way of working or writing in our own work. And here is as an example of a really, well, I want to say perfect example of what a project website with data and code could look like with a published paper. So here, they're talking about what is the website, and we've got all the codes related to the results and where we can find the data. So let's say we click on this. Well, in fact, well, we could see all like where the data were, basically. So if I want to go back to the presentation, this is here. That was it. So the links are going to be down in the description. But it was just to showcase that people during their PhD can do amazing things. But why isn't it everyone already sharing or doing open science? Well, first, we could argue that there's a lack of guidance in how to apply open science at the individual level. And we think it's true. In fact, that's why we are involved with Open Science UMontreal, basically because we think we can make some new content or help each other doing science more openly. So as a community, I think it's fun. Well, it's more interesting to learn together than each on our side. But it does require more efforts, and the funding and the evaluation structures also offer no incentives for now to justify the extra efforts. And there's also some legal reasons. So you may not want to share some data because of privacy concerns. But that being said, what can we do about this? Well, we could change the incentives. For sure, as students, it's hard to change the incentives, but if we don't believe that the system is going to change and we don't act now in doing so, by believing that it's going to change, and then we should start working openly right now. So if the incentives are aligned with the open science mission or movement, well, we're going to be ahead of a lot of people. So to change a system, well, first, people had to make it possible. So we now have the infrastructure. We had to making it easy. So right now it's easier than what it used to be. It's not getting more normal to do open science, and this is why like awesome like communities like Awesome are doing work. So it's basically just to normalize doing open science. So, but now we need to make it rewarding. So publication won't be the only currency to be a successful researcher. So there will be ways to evaluate how research contributions are as the research contributions are available. So right now we will, and I'm sure we can right now, track a lot of different things. So if we open the whole research circle or cycle, well, we will be able to maybe not rank, but evaluate researcher according not only to their publications, but to whatever they've provided the research community. And what will you gain if you do open science as a researcher? Well, there's been a couple of evidence now that there's a higher citation rates for open access papers. Often open work are going to get more media coverage because it's not behind paywalls. And also you're going to retain your author rights, which is really great because now you can authorize anyone to reuse or modify your research or your work from code to data to results. And most importantly, you're going to feel good about yourself, and you're going to be ready for what is coming, because yes, we're going to need to be compliant with the new policies that are going to be put in place soon enough. So instead of being at the tail, well, we should just be ahead of everyone and be already knowledgeable about all the tools we need to use to properly do open science. So just to conclude, there's more than one recipe. Of course, we've mentioned a lot of things about open science tools and ways of doing open science. But in order to help us decide which ingredients we should focus on, well, if you can fill this little survey, it's a 5-minute survey. It's going to help us to decide what to focus on and do some more videos or workshops on. So in the end, as I said, it's not a single recipe, but we should see it more as a potluck. So basically, everyone can contribute whatever they can, whatever they are willing to contribute, and they can take also whatever they want. So we shouldn't force people to be open from like starting from writing grant to the results, but we should simply work, as I've mentioned earlier, as open as possible and as close as necessary.
Yeah, well, this is just a reminder that if you want to contribute to our list of resources, you can submit pull requests, and we'll make sure to merge everything that you add.
So this is the end of our talk. Well, I would like to thank you for watching us until the end. If you have questions, reach out to us on either Twitter at OSMontreal or info@osmontreal.ca. And we also have a chat at chat.openscience.ca. So thank you.
Thank you.